Assalamu alaikum, my dear students. Hope you will be fine and okay. Uh, Today is the start of our new unit 15, the alternating current or the AC circuit. Most probably, we will study here in this chapter. So let us start with the our lecture with the name of Allah Almighty. Bismillah ar-Rahman ar-Rahim. Our today topic is the sinusoidal alternating voltage and current. So first of all, I want to introduce to you with the AC terminologies, the instantaneous value, the cycle, the time period and frequency, the peak value, the average value, the RMS or the effective value. Sometimes it is also called the virtual value. This is also called the virtual value. This just stuck my mind. The phase of AC and phase difference, the alternating quantity representation. First of all, I would like to tell you that it is more practical than theoretical. Here, we are more practical than theoretical. Than theoretical. Here we are interested in the use of the AC current rather than in the production of the AC current, right? So let us start with our topic. The first topic here is the instantaneous values. That what are the instantaneous values? The instantaneous values. Look, as you remember in the previous chapter that I told you about the AC current, and if I just give you a kind of review, then I told you that such a current or voltage which which continuously changes its magnitude its magnitude its magnitude and polarity many times in a second. That is called the alternating current. So we have the alternating current quantities, two current quantities. One, we have the alternating voltage, the alternating voltage, and one we have the alternating current, right? Usually they are it is denoted by alternating voltage is denoted by small v, and it is by small I. Usually the capital I stands for direct current only, right? So the direct current can be represented by capital I, while the alternating can be best represented by small I, so that we can differentiate between the two. Now, look, we have rather even pulsating current also, which quickly contract and expand, as you see here in this diagram. Okay, now if I just draw the diagram, then you will see it here. Like, look, if I just draw the diagram, you see here, look, this is our y-axis, and this is our x-axis, and this is what all the things change in time. And you may take the current or both voltage along the vertical axis. Okay, so here as I told that we have the two different quantities. Then we wish to study the instantaneous values of these quantity first. Now look, the instantaneous voltage, which I will label as VI, then if you remember the most famous equation there in the previous chapter that I told, like for example for the EMF, let me first write that one, okay, so that you can have the better understanding that the induced EMF was equal to epsilon naught into sine theta, if you remember, r, if you remember like this, it was sine omega t, or it was like this, e into sine 2 pi f into t. And that was when we were studying the production of the induced EMF like that. So see here, look, now if we want to be practical, then we will just do it in terms of potential difference. Here we have the induced voltage, that is V, and I will label it instantaneous, right? And that is the V max or V naught. I will write, you see the V max, the V, if you see anywhere like these thing, the V naught or the Vm or the V max, it represents the maximum constant value that the circuit can attain. Okay, so the V max into the sine 2 pi f into t. So definitely, what does this means? That your V, that it depends on what, that it depends on t, right? Why? Because the frequency is constant 2 pi, you already know the Vm, the maximum value, it is already constant. And if you remember, I told you in the previous chapter that it is equal to Nawab, number of turns in the coil, area of cross section, angular frequency in beta. So instantaneous value is in fact the value of the alternating quantity at any instant of time. The value of what? The, that it is what? The value of AC quantity at any instant of time, at any instant of time is called the alternating quantity. So here you see that, look, if you just see this graph, and for the green you see, look, we have this any value, you choose at the value at the point A, at the point B, at the point C, D, E, F, any of these value is the instantaneous value, right? And they are what? They are the, any the values at the point A, B, C, D, E, F, they are the instantaneous value of the alternating current, right? Sorry, voltage. Similarly, for the alternating current, I wouldn't like to go any further, but very simple. I will be equal what? It will be equal I naught or I max into sine 2 pi f into t, right? Or just like you can also write the I instantaneous in the small, as I told you that it is usually denoted in the small, so better because it is changing, so that will enough to write I into I am rather subscripting it as instantaneous I maximum value into sine, you can also write 2 pi by t into t, where t is the time period. And if you just look into the graph here, this is just one time period, and it will be equal to 2 pi radian, and it will be half of the time period, that is the time taken for which the coil turns half cycle of its rotation. And here it will be just pi, and then definitely here it will be t by 4, here it will be 3t by 4, and definitely in the term of pi it will be pi by 2, and it will be 3 pi by 2 for this. Okay, so you see that look, the rest will be divided into this. So that is what the, so any at any instant of time, and for example look, your t may take the value 0, so you see what will happen at 0. It may take the t by 4, t by 4, it may take the value of t half, and may take the value of 3t by 4, and may take the value of t, right? So you can see that look, the alternating current quantities now put the t for the various value, and definitely here you see that it is for 0. Let's say it is 0. For the t by 4 it is maximum, the positive maximum I max, right here, that is your I max, like this is the maximum value I max. Okay, and it is I max. Okay, and here for the t by, for the t by 2, this produce 0, this will produce you 0 value, and for the 3 by 4, as you see it here, here it will produce, for example if I take the I, so here it will be I max, but in the opposite direction, current flowing in the opposite direction, maximum current, but in what, in the opposite direction, I max. And here a one complete time period like this, a 2 pi radian or a t is equal to 1 time period, you have again the value as 0. So this might be better for your MCQs. Okay, and this is the same here, same here. Okay, now the next one is the peak value, the time period and frequency, that is very childish. Frequency and the time period, you already know from the previous chapter, it is the time taken to complete one cycle is known as one time period. Frequency is the number of complete cycles per unit time, and you already know it is measured in hertz. And the AC which we will be studying here is has the frequency of 50 hertz, round about like that. And the time period, you already know the reciprocal of what, it is the reciprocal of the frequency, and it is measured in seconds, right? And it is measured in what, the frequency, which is the reciprocal of the time period, measured in hertz. Okay, so I don't want to discuss that anymore. Now look, the peak value, that what is the peak value. So for the peak value, peak value. Now, what is the peak value? The peak value is in fact the maximum value reached by AC quantities. Yeah, the maximum value, the maximum, the maximum value attained attained by the AC quantity, by the AC quantity is called the peak value, is called the peak value. Sometimes it is also called the p value, the peak value. And here the peak value will be represented by Im or Vm, the maximum values. So here look, the peak value, I just label this and this, and for the voltage, right, you can do that. Here the peak value is this one in the graph. This is the peak value, right? The peak to peak value. So you have the positive peak value and you have the negative peak value. Remember, the positive half cycle of the AC current is as important as the negative half cycle, right? Working performance is purely the same. They produce the same heating effect. The difference is in the positive half cycle, the current flows in one direction from 0 to T half, right? And in the negative half cycle, the current flows completely in the opposite direction from T by 2 to T. So you must remember. And then there is a peak to peak value also, and the peak to peak value is from one peak to another. Okay, but that is least important here. The next value is the average value. The average value. Now, what is the average value? The average value. The average value of the alternating current is, let me first do this so that to create more space. Move the diagram. Okay, the average value is obtained for any AC quantity. The average value is obtained as the total area under the curve. Total area under the curve. Under the curve, which for one cycle. Okay, for one cycle of AC. One cycle of AC. Divide by the time period for this, the time taken for this. So definitely the time taken is nothing but it is the time period, right? So that will give you the average value of the AC quantity. Now the next one is the most important one, the RMS, or the effective value, and here we will much focus on it. The RMS or the effective value. RMS or effective value, are effective or the virtual value. The effective value. First of all, I just want to explain the need of this value, that what really it is, and then I will be explaining this to you, that what really the RMS or the peak to peak value mean. Okay, first of all, let us see the problem here. Okay, and what is the problem here, which you will see now. So see here, look, if I just make this for you, look, if you know, we use what we use the ammeter for measuring the value of alternating current or voltage present in the circuit. Now here the problem is that though we have the AC measuring meter also, but if you just look to over one average cycle of the AC from 0 to one complete time period, from T by half n to T by 4 n to 3T by 4, right? And similarly pi by 2 as you see, or pi as you see, or 3 pi by 2 as you see here in this diagram. Now the question is that when you place the AC or the meter, for example, when you place the M meter in the circuit, the M meter in the circuit, any AC circuit, the question is that we don't know that at which time it will attain its maximum value, right? Sorry, that at which time the AC will be passing through its switch value. We don't know whether the meter will read this value, whether it will read this value, whether it read this, it read this, it read this. It depends, right? The generator, the coil of the generator is passing through which stage of its motion at that instant of time where you measure the current. So that is the bigger problem. Okay, now for that reason we use the RMS values, and one thing must be very sure, that for the RMS values or the effective values, that it is, these are the values, these are what, yeah, that is the ammeter, the ammeter, the voltmeter. When you place in the circuit, AC circuit, always measured, they always measured the RMS values, the RMS values, rather than the maximum or the minimum, rather than what, rather than the max or minimum value. And the second most important is that the RMS values are, the RMS values, the RMS values are the AC equivalent, the AC equivalent of the DC, right? Because we have two currents, so they are exactly in matching. So whatever the effect the DC current, a particular DC current produces, here you see, look, the red line here, as I told, this is a direct current DC, right, which has a constant value, right? So whatever the DC current has the effect, the same equivalent effect in the AC will be that of the RMS value. Okay, the RMS means RMS, root mean squared value, root mean squared value. For example, look, IRMS, to be very simple, I want to tell to you that what is this value, the IRMS. The IRMS value is the root mean squared value, and the root mean, and the root, it is the root, the mean, the squared value, first root, okay, like this. Second, the mean. So what is, for example, this is the simplest way I can do for you, okay? This is the maximum mean value I naught. So what I'll write here, I max, maximum, root, and then the mean value, because you have the two maximum, the positive maximum and the negative maximum. So 2, okay, and squared, so the root means squared value, okay. And then we have what, and then we have the root, the mean, root mean squared value, okay, sorry, like this, okay, because the root, the RMS root mean of the squared value, so I must be squared, okay. And what is the answer? The answer is Im into 2 under the root. So this is the IRMS value, right? And this IRMS value on the graph, I'll be denoting it, it is just like this, okay. This is the IRMS value. Which value? The IRMS value. How? Because look, if I apply this, see here, the first, the Im square. So if this is Im, then what will be its square? Definitely its square will be like this. So this is your I square, okay. And then they, after they half of the I square, remember, it is not the half of these two, right, but it is the half of the square value. So definitely that half will be somewhere here, okay, like this one. And then what you take, then you take the square root of that value, and then it comes right over here, okay. So this is the root mean square value. This is what I avoided a very long mathematical setup to introduce to you to this thing, okay. And then let me go there and do some mathematics, and maybe now you will that will be very easier for you to understand here, okay. Now let us see for the RMS values. The RMS values, as I know, that look here, what I can write for the RMS values, you will see it right now. As you know, that in as you know that I is equal to what? For any value I is equal to what? Im into sine omega t. Okay, sine omega what? Sine omega t. And but we also know that the if the current is passed through any resistor or any load resistance, then the power delivered by this any circuit or the power delivered to R. Yeah, power delivered across R, any resistance. So this power delivered will be equal to what? P will be equal to, it will be equal to I square R, right? And then what I can write, that it will be the Im into sine omega t whole square into R, and this will be equal Im square into sine square omega t into sine square omega t into R. It will be like this. Now, because the current is squared, power is always positive. Since the value of sine omega square varies between what? Look, you know what is sine of 0? The sine of 0 is what? It is 0. And what is sine of 90 degree? It is 1. So over one complete cycle, if I just make one complete cycle like this, as you see here, look, for this one maximum, as you see, the average value of the sine square omega t is equal to 1 over 2. The average value of what? The average value of the sine square omega t is this sine square omega t. It is equal to what? 1 over 2. It is equal to what? 1 over 2. Why? Because this is the minimum. This is what? The minimum value. And what is it? This is the maximum value. So when I just take the when I just take it, then what it will be? Its average value. It will be definitely 0 plus 1 by 2. So it will be 1 over 2. Okay. Now the as we know that this is equal to 1 over 2, so from this equation, from 1 I can write that let me just do it. From 1 equation, yeah, let me do it here. From this equation 1, from 1 I can write that P is equal to P is equal to what? That is Im square into, we have the R, and since you know sine square is 2, so it is equal to Im square 2. Okay, so that is what? That is equation number 2. So if you remember, as I told, that as the emitter reads the what? The emitter always read the RMS value, the RMS values. So the average power delivered to the circuit must be equal, P must be equal the IRMS square value into R. Clear? It will be equal to like this. So now this is equation number 3. Here from 1 and 3, from 1 and 3, what we can write, both the same. So IRMS square R equal Im square 2R. And if you just simplify this, then the IRMS will be equal I max by 2 under the root. So here you now know that IRMS is equal to Im by 2 square root or 0.707 I max. Or if you know the IRMS value, because the meter always read that, then Im will be always equal to 2 under root into IRMS. Clear? it will be like this. And similarly, if you just find the root mean square value, another thing important, even if you don't understand this, a very simple way I'm telling to you, you take all the mean value of sine of these angles, right? And the answer will be definitely this one, 0.707 IM. Okay, so that is another quick and easy way of learning it. So, but remember in radian, right? Now, for the voltage, Vrms must be equal Vm divided by 200. So if you know the RMS values, which will give you your ammeter or voltmeter, you can find the Imax. Once you find the Imax, you can find the instantaneous value at any instant of time. Okay, now I plan to teach you the phase of the AC and phase difference and alternating quantities representation also, but the lecture will be then too much lengthy. Okay, so I postpone these two topics and I will carry it to my next lecture. So inshallah, I will explain phases of AC and phase difference and alternating quantities representation. So they are not that much simple so that I can finish it within 2 or 3 minutes. I want to explain it in greater detail and more elaborately because we need it everywhere, right? And it is extremely important. So see you in the next lecture, inshallah.